like extra example number 17. Let me pull up extra example number 17. There's quite a bit in here. But let's look at example number 2. We're not going to solve example number 2. We're not ready to solve example number 2. But I want you to see the sort of problem that we want to learn how to address, how to solve. So it says, let me just tell you what it is. So it says, calculate the final equilibrium temperature. Equilibrium temperature, that's when you have thermal equilibrium, that's when everything has the same temperature. Final temperature. When 150 grams of steam, that's water that boiled, initially at 100 degrees Celsius, so steam at 100 degrees Celsius, certain amount of that, 150 grams, is passed into 200 or mixed with 200 grams of liquid water. I mean, it's water, I guess I shouldn't say liquid. So with 200 grams of water and 25 grams of ice, both the water and the ice initially at 0 degrees Celsius in a container. So we have this steam at 100 degrees Celsius. We know how much of it there is, I think 150 grams, right? And then we have this water and ice, both at 0 degrees Celsius. And I know how much ice and how much water I have, right? The masses over there. And then I mix the steam at 100 degrees Celsius with this water and ice combination at 0 degrees Celsius. So what will be the final equilibrium temperature? Okay? And I'm mixing 3 things, not 2, 3. Ice, the water, initially at 0 degrees Celsius, and the steam. Right? So we want to be able to solve that problem. Right? So there's a reason why I set the initial temperature of the steam at 100 degrees Celsius. Because gases are, you have to be more careful with gases than when you consider solids and liquids. Because the gases can expand. What happens is that liquids are usually incompressible. Like if you have a water and it occupies some volume, it's like you try to squeeze it, you're not really gonna make that water take up less volume. I mean, they're pretty much incompressible. But gases, you can compress gas, right? You can, in the gas, the molecules or atoms are farther away from one another. There's a lot of empty space in between them, and you can compress the whole thing, reducing the volume between them, and so they are compressible. So the relationship between temperature, pressure, volume, and so on for gases is different from like liquids and solids. So gases, they're treated separately. One has to be more careful. There are other things to consider that you do not consider generally for liquids and solids. And so there's like a whole chapter on gases, like chapter 18, chapter 19. They're dedicated to gases, right? So in this chapter, we are mostly going to focus on liquids and solids. So the only thing that we're going to consider about this gas over here, this steam, is that as soon as it loses energy, it's going to turn into water without going a change in temperature. So there are ideal gas laws and so on, but we'll talk about them separately. You'll see why in a later chapter. So I force this steam to not be above 100 degrees Celsius, because how you cool down steam from, let's say, 105 to 104, 203, there's more to it. I would have to specify more in this problem. So I just stayed away from that. I still consider steam so that it could condense into water, but right away it loses temperature, and then the steam is going to turn into water right away. But anyway, it's like this chapter is more on liquids and solids, and we'll deal with gases later on. So that's one problem that we want to address. Okay, so going back to notes here. that's the section that I'm skipping. I mean, I wrote things in there, but if you read chapter 11 first, and then this will make a lot more sense. Okay, so heat. Right? Remember, I don't know, I think the title of this chapter was temperature and heat. So, so I want to talk about heat. So what is heat? So heat is energy. Heat is energy. Measured in the metric system in what units? Joules, correct. So heat is thermal energy transferred from a region of high temperature to a region of low temperature. So the key word over here is thermal energy in transit or being transferred. Yes? So if I have, for example, if I consider, for example, a rod, suppose this is a metal rod. So this is a rod. And suppose this I put on fire. Fire, fire, fire. So this is hot. And this end over here, I put it on ice. Right? So, so that this is cold. So this end of the rod is, and this is solid, right? This is solid, right? So what happens is that the atoms in this end of the rod will jiggle more vigorously. The atoms here, less, more vigorously. What are the atoms on this side of the rod going to do to the atoms next to it? So if this is jiggling, it's going to make the one jiggle next to it. And then this one is going to make the one next to it jiggle, and jiggle more, and jiggle more, jiggle more. So the jiggling is going to go zzz, and then, then this is going to be jiggling more vigorously. So it's like, but the atoms from here don't go over there. The atoms stay here, right? It's like, you're all in a line, right? And then you shake him, like, wake up, don't sleep in this class. And then he shakes her, and wake up. And then, but you don't go there, right? And you don't go to her. And then she shakes him. And so the shaking got transmitted to the back, even though you never went over there. So that transfer of shaking, that's the energy that's being transferred down the rod. So this is thermal conduction. Thermal energy is being transported, it's being conducted right through the material. Right? So when that energy, thermal energy, is in transit from hot to cold, that's heat. Heat energy. Is that heat energy in transit from hot to cold? Now, on the other hand, if I have a rod like this, right? So this is the rod, which is a solid. But the temperature is the same throughout. Same temperature. Whatever the temperature is, right? Same temperature. Then there is, if this is hot, and this is just as hot, there is no thermal energy going from hot to cold because everything is at the same temperature. So therefore you don't have heat in it. Now, to us, if you consider the surrounding environment, if this is a hot rod, let's say this is hot, and the air in this room is, cooler than that, then what will happen is that thermal energy is going to flow from the rod that's hot to the cooler surrounding air. And that's energy being transferred from hot to cold. So that you can call heat energy. You say it radiates heat. Right? So then you can go like this. So that you can call heat. Now, people say that because the radiant energy comes from here, or from this object this way, well, that energy came from there, so therefore it has heat. But you see the problem with the definition of the word heat? Huh? It doesn't have heat because everything is at the same temperature. But it is hot relative to the surrounding cooler air, so energy is going to flow from the hot to the cold. That energy from the rod to the cold object is heat. That is energy in transfer. So instead of saying or describing this object as, I'm going to give you something here with a lot of heat, what I should really be saying is I'm going to give you something that's hot. something that has a high temperature, especially if all of it is at the same temperature. Now, I can give you something that has heat if this is hot and that's cold, and there is heat energy in transfer from one end to the other. But if everything is at the same temperature, I should really be telling you, I'm going to give you something that's hot. Something that has a high temperature, not something that has a lot of heat. Even though what will happen is that because it's the same temperature throughout, but it's hot, right, and it's cooler over here, heat energy will, that heat energy is the energy transported from the hot object to the cooler air. But then you say it's like, it came from there. But I don't know, it's a word that is misused a lot. Heat, right? A lot of people use the word, heat when they mean hot. Heat is the energy in transit. The key word over here is the energy that is being transferred, right? So I put that in italics. And by the way, the energy could be transferred, right through the jiggling of atoms to atoms next to them, and so on, or an energy could also be transferred by electromagnetic waves. So, for example, the sun is hot. The earth is cold relative to the sun. The surrounding vacuum of space or so is cold relative to the sun. So thermal energy goes from the sun to the surrounding space. But that happens in the form of electromagnetic waves. It's energy radiated away from the sun. You don't have like the sun over here, hot sun, and cold earth. There's no tube or rod or conductor connecting the sun to the earth that jiggles, and then the jiggling energy is being transferred through the rod from the sun to the earth. That's not what happens, right? We don't have a tube or rod or something connecting the earth to the sun. But there is energy transfer from the hot sun to the cooler earth, and it's by electromagnetic waves, and we're going to talk about that in this chapter. I believe it is later on. So I just want you to understand what the word heat is. I mean, it's what we used. Heat, well, it's energy. It's energy in transit, because it is energy in the metric system, it's measured in units of joules. But there are other units of energy. Another unit is the calorie. It turns out that in order to, if you have water, for example, and you have 1 gram of it at 15 degrees Celsius or so, right? And I ask the question, how much heat energy needs to be transferred into this water? How much heat energy needs to be transferred into this water so that the water goes up in temperature by 1 degree Celsius, so that now it becomes, water, 1 gram, now at 16 degrees Celsius. So the heat energy that you need to add, and Q is the symbol for that, for heat energy, is 4.186. No, 4.816. No, 4.186. It's 4.186. Yeah, 4.186 joules. So I guess instead of working with decimal places for that amount of energy to raise the temperature of 1 gram of water by 1 degree Celsius, right? People define this as 1 calorie. So a calorie is just a unit of energy, and it's defined as the amount of heat energy that would have to be transferred into 1 gram of water to raise the temperature of that water by 1 degree Celsius. 1 gram of water, 1 degree Celsius. I guess we don't need this anymore. Now, this is interesting. There is this other unit of energy called the diet calorie. It's tricky though, which is equivalent to 1,000 of these guys over here. that would be there for 4,196 joules, right? But here's the thing about it. It's a measure of energy release when you eat some foods and so on. There are some details in there that I'm not too familiar with, but if I like those Snickers bars. If I buy a bar of chocolate, for example, I don't even know what the number is, but I wouldn't be surprised if it's like 500 or so calories. Those 500 or so calories are these guys with a capital C. You may be fooled thinking that it's the smaller ones. But if I say calories, I don't specify, calories with a capital C. Because